A good day I bid to Dr. Roslina. My name is Sorna Valminichmanan and my group partner is Omiyal Yoganathan. Today we will be presenting about the dry etching process.
In nanofabrication, etching is the process of removing regions of deposited films or substrates. Two of the major processes used in nanofabrications are deposition, where the process of laying down the film, and lithography, the process of patterning the mask, usually films of the photoresist. Basically, dry etching is vapor or gas phase etching. Etchants come in as a gas and byproduct leave as a gas. So having a volatile byproduct is essential for dry etching. Down here is the diagram of the basics of dry etching. Here we have a wafer. We have a reactant indicating fluorine coming down the surface, etching reacting with the surface, and a byproduct silicon tetrafluoride coming off. Rather than starting off with fluorine, we start off with CF4, which is a very stable gas, and we use a plasma to break up the gas and generate ions, electrons, but also reacts free fluorine.
Now, let's take a look at the benefit and disadvantage of dry etching. Let's take a look at the advantages first. There are numerous benefits towards dry etching. Some benefits include less waste that needs special disposal, better critical dimension control, cleaner surfaces, and reduce in corrosion of metal feature of the substrate. However, there is some inconvenience in using dry etching in that it is required specialized equipment to handle the plasma and the reactive gas. Other than these techniques, which are divided into its own basic categories, dry etching can also be categorized by how the plasma is set up, the system used in dry etching, and how plasma is generated. The setup. The two main types of setup used are glow discharge etching and ion beam etching. In glow discharge etching, plasma is produced in the same vacuum chamber where the etching process occurred. Meanwhile, in ion beam etching, plasma is generated in a different chamber. The system used in dry etching here referred to the amount of wafers the equipment can handle at the same time. Some dry etching equipment can handle batches of wafers, while other can only handle a single wafer at a time. These two types of system, the batch reactor and the single wafer reactor, have its pros and cons. However, given the right condition, both reactor can give good results in the etching process. Plasma generation. The generation of plasma is divided into four types. From DC field, which is 0 Hz, from AC field, 50 kilohertz and up, from radio frequency, field 13.6 to 27 megahertz, and from microwave field, 300 megahertz to 10 gigahertz.
Now, we will look into edge profile control. Firstly, it is used for removal of blanket layers, such as we can use it for removing resist after an etch process. Secondly, it is for patterning. In patterning, we use a mask to block the reacting ions so that we can duplicate a copy of the mask in the material on the surface of our wafer, and usually the mask is often a photoresist. For the first diagram, here's a substrate with a uniform film, and we want to pattern that film at the top. And the way we got there first is we put a photoresist layer and pattern it typically with optical beams or electron beams, and then we expose it to our plasma etching process that selectively removes the film in the exposed open areas, and then we remove the photoresist film. So now we have our patterned film on our substrate. So typically, edge profile is critical to the structures we want. By profile, I mean the edge of the film. So for the for nanostructures, we want to have a high fidelity reproduction of the film of the structure, a patterning in our mask layer in the underlying structure. Whereas in other cases, we want to have some slope and maybe a little bit of undercut, typically because of step coverage issues. So here we want to show the case to define as anisotrophic etching, which is completely vertical etching and it completely replicates the mask in the film. The second case is isotrophic etching, and this is where we got some pure chemical etching where you have to undercut equal to the etch depth. So if I go down a nanometer thick, I go sideways a nanometer thick. And this can be very useful for some structures, but we really have a difficult time getting step coverage. And lastly, we want to talk about the near anisotrophic or directional etching. This is probably a little more typical of a lot of things we are going to actually see. We have a little bit of undercut and some slopes. We do it intentionally to get some step coverage.
Selectivity Selectivity is the ratio of the etch rate of the material to be removed divided by the material to remain. So let's see here, this is my diagram of the substrate, the film and the photoresist pattern. So I've removed some of my photoresist and I'm etching the material. The reason I want selectivity is I don't want to lose this mask material before I get all the way through the film I'm etching. The second selectivity is when I go all the way through the material and I hit the substrate material. Selectivity is very important if I'm etching a gate over a gate oxide.
Now, we will look into basics of plasma. So here's a vacuum chamber. We have electrical power coming in, gases going out by the way of the vacuum pump. I see light coming out, and in the plasma we have neutrals, ions, electrons, and radicals. Plasmas are steady state process results after breakdown. The electron gain energy from the applied field power electrical field going to heat up or give energy to the electrons. The higher the energy in electrons, whose collision will have ionization and excitation and fragmentation of our source gas molecule. In plasma region, we mainly see glow. We have a charge balance where the density of electrons one going to be balanced to the density of positive ions, mainly neutral species. The glow is from the decay of short lifetime excited species, which is nanoseconds. Any place you see glow, there is where electrons are hot. They are basically breaking down and fragmenting the gas in it. If it's dark, we don't have any hot electrons. Now we can look into why we have to use plasma for etching. We can use it for generating local sources. We showed etching of silicon with free fluorine, where free fluorine is very reactive and it is much easier and safer to generate the fluorine locally using the plasma. Second, the plasma etching is often much easier to do than wet etching. For example, wet polysilicon etching is very difficult to do with a mask layer. Next, we can get very high aspect ratios using plasma etching. Aspect ratio is the ratio of depth divided by the width. Etch into silicon with aspect ratio of 40 to 1, the given in the diagram. In plasma etching, we have ions which can be used to bombard the surface and other useful things like the ion can clean the surface and remove oxide polymers left over from the lithography before etching process. They can also activate chemical reactions. So, all this while, we talked about plasma. So, what is plasma? Plasma is ionized neutral gas with equal number of ion and electron. It is essential in dry etching process as plasma have the capability to separate the gas into neutral ion, electrons, photons, and reactive radical to be used in the bombardment of substrate surface, resulting in an etched surface. While DC plasma is generated when voltage is applied to a neutral gas between cathode and anode. This is called glow discharge plasma. When a voltage charge is applied, high velocity electron collided with the neutral species gas, which can result in either inelastic collision or elastic collision. When inelastic collisions are made, electrons are knocked off and ionization of the molecule occurred, resulting in a positive ion and free electrons. The free secondary electron will collide with other gas molecules, increasing the supply of energized positive ion and free electrons and the glow that is often seen in plasma. The process will continue reaching electrical breakage, a process where the insulating material between both electrode is filled with electron and positive ion to the point that insulating property is destroyed. The process will reach an equilibrium when the rate the electrons are lost is equal to the rate that is electrons are gained.
Regions and characteristics in DC plasma. Plasma is composed of bright and dark region. As mentioned earlier by Omia, electrons glow when it is either going through excitation or relaxation. As seen in the figure below, these regions usually alternate back and forth, as electrons do not have enough energy for excitation in the beginning at the cathode but gain those energy while it is accelerated away from the cathode, resulting in the first glow region, the cathode glow. As the electrons become excited, it loses its energy from the same process, resulting in the second dark region, the cathode dark space. The process switches back and forth from the cathode glow to the cathode dark space. These regions are divided into two sections, the anode layer and the cathode layer. The anode layer started from the positive column to the anode dark space. The positive column have a few positive ion and the electric field provided the electrons enough energy for it to go through the excitation and relaxation, resulting in the soft glow. The anode glow is the brighter region when compared with the positive column due to the stronger electric field in this area. When electron entered the anode dark space doesn't have enough electrons to provide sufficient excitation to glow, resulting in another dark space. A cathode layer includes several regions, starting from the acetone dark space to the negative glow. This section will briefly explain two regions contained in the cathode layer, the cathode dark space and the negative glow. The cathode dark space contains a high concentration of positive ion. This occurs because the ions have bigger mass than electron, making it move toward the cathode slower than the electron that is being repelled away from the cathode. The cathode dark space also contains the greatest amount of voltage drop when compared with other regions, earning the name cathode fault. Due to this region having a strong electric field, when the positive ion collided with the surface of the cathode, the impact caused an emission of the secondary free electrons.
Paston's law states that when a voltage of about 3 megavolt meter negative 1 is applied to neutral gas, electrical breakage occurs resulting in the creation of plasma where passage of high current is created between the two electrodes and followed by a spark discharge. When the spark discharges in a localized location, it is called corona discharge and the current created between the two electrodes due to electrical breakage is called arc discharge, which is the process that is desired. For us discharge, you can think about lightning bolt. If we look into Paston's curve, it is worth noting that as distance reduces and pressure increases, the amount of voltage required to cause breakage is reduced until it is the minimum voltage that can cause breakage. As pressure continues to increase and distance continues to decrease, there is not sufficient space to cause ionization, and the high pressure increases the amount of collision to the point that energy is lost to the point that it cannot cause ionization. To solve this, voltage have to increase to cause breakage, resulting in the sharp curves seen in Paston's curve given.
RF plasma. In RF generated plasma, the polarity of the electric fields constantly reverses twice every cycle. Due to the constant change in the electric field, this doesn't become a problem if the frequency of the AC is high enough such that half of the period is less than the charge up time required by the edging material. RF produced plasma, there is no need for the free secondary electron as the plasma itself is self sufficient. Similar to DC generated plasma in many ways, the RF plasma also follows Paston law in breakdown voltage, and the neutral species also far outnumbers the electron and ions. Usually, Vp is very small to prevent sputtering on the anode, so that neutrality in plasma is retained. Furthermore, to maximize the sputtering effect on the cathode and minimize it on the anode, the cathode area is smaller than the other area receiving the discharge. but usually large enough to hold several wafers so that they can all be etched simultaneously at the same time. A good etching results from high quantity of low energy ions and low pressure radical provided by ionization, which resulting in a lower etch rate for the trade-off of good selectivity, uniformity, and etch profile. It is also believed that there will be less damage done by the radiation from the plasma or completely remove the effect of radiation.
Let me show you symbolically the etching process and role of ions. So here on the top we have an electron colliding with a source molecule generating a free radical. This free radical then diffuses to the surface that I want to etch. It absorbs in the surface, and if it's like chlorine, it just sits there. But if we have an ion come in, the ion can actually create sites by breaking bonds, let's say silicon bonds. And when the bonds are broken, the absorbed agent can then react with the material, let's say silicon, and then form a volatile product of led to a chain reaction of spontaneous reactions. And so the product then comes off, and we are net removing the, let's say, silicon. We are removing the silicon from the surface.